Because we're in 2 dimensions, we only care that bearing A exerts a vertical force. We don't care about the force coming out. So there'll be a force at A. There'll be a force at B from that bearing. A is a thrust bearing, B is a journal bearing. So remembering back to bearings, a thrust bearing prevents the shaft from translating through the direction of the shaft. So the bearing at A prevents motion left and right because it's a thrust bearing, and it prevents motion vertically because the shaft can't move in the Y direction. And at B, we have a journal bearing. A journal bearing allows translation of the shaft through the bearing, so it does not prevent motion in what I'm calling the X direction, but it does prevent motion in the Y direction. Both of them prevent motion in the Z, but we don't care about that for this problem. So those are our reactions. We have an applied load of 900 newtons from that belt at D. And we have a distributed load acting on the shaft as well. So we need dimensions for this. So looking at our free body diagram we just made for the external picture, we have AY, AX, BY. We have 3 unknowns. It's a 2D rigid body, so we can get 3 equilibrium equations out of it. Equations are next. From the free body diagram, we can sum forces in the X direction. Because we're in equilibrium, they're going to sum to 0. So based on our free body diagram, the only thing we have in the X direction is AX. So AX is going to be 0. If we sum moments around A in picture 1, we're going to be able to find the unknown BY. So summing moments around A, what are the sum of moments around A going to be in the first free body diagram?
Negative 24 newtons. Be 600 times the 2 meters at the 2 meters away from the rotation.
Okay, a total of that, right.
Yeah.
So the distributed load, first of all, we have to find out what's the equivalent force. That's going to be, because it's a uniformly distributed load, it's its intensity of 600 times its distance it acts of 2 meters. So we're at 1,200 newtons of force. And the equivalent location it acts is going to be at center point. So 1 meter from its edge, which is another meter from A. So 2 meters times 1,200 newtons is 2,400 Newton meters due to the force, the equivalent force of this distributed load here. Right, and it's going to be negative because it's acting in a clockwise rotation around point A. So I'll write out the pieces of it here. So it's a negative 600 is the intensity times its length it's acting on, 2 meters, times 2, because that's how far the center point of it is from point A. Again, it's going to be negative because it's acting clockwise around point A. Right, what else acts around point A?
BY.
Right, BY. Right, a distance of 4.5 times BY, since BY is going to be acting counterclockwise around A. Yep. 5,400, right, 6 times 900, 5,400. So 6 times 900 I'll write it out here explicitly. All right, so this is the total moment around A. AX and AY do not contribute to the moment around A since their moment arm is 0. So by taking the moment around A, the only unknown we have is BY. So we can solve that BY is going to be 1730 newtons. Finally, we can take the sum of forces in the y direction to get AY. In the y direction, we have AY. We have BY, both of those point up, minus a 900 pointing down, minus a 600 times 2, also pointing down. From equation 2, we solved that BY was 1730 newtons, so the only unknown left is AY. AY is going to be 367 newtons. BY and AY are both positive, meaning that our assumptions were correct. They are both pointing up. Questions on the first step here? Okay, so this is what we did in kind of the first half of 211, that external problem. Now we're ready for what we did at the very end of 211, going inside and looking at the internal forces acting at C. So remember, point C is at the center point of where that distributed load is acting. In the interest of space, I'm going to erase this free body diagram. And now jump to a second free body diagram, the internal picture. Yeah.
How did you get 367? Shouldn't it be 370?
I think from the rounding, I solved them simultaneously. I think this was rounded after the fact. So this really was like 1727, I think, or 1733. So I actually didn't do this by hand, so that's probably why I'm getting these answers. In this class, for those of you who did not have me last semester, 3 or 4 digits of precision is good for your answer. So if you reported 1730, 1727, or 1733, any of those answers will be fine for me. Please don't give me 8 digits of precision. Just because your calculator gives you 8 digits, I don't need to see 1730.543291 because those numbers are meaningless. I won't mark it wrong still, but I will cross it off in red pen. So that's pretty bad. Any questions on the external part? All right, so jumping inside, this is where we make that internal cut at specifically C. And specifically, we want a vertical cut that passes through there. So remember from 211, when we make that cut, we have the option in our picture. We can take everything to the left side of the cut, so that way include what's happening at A, or everything to the right side of the cut, so that's including what's happening at B and the applied force at D. We're going to get the same answer, the same magnitude of answers at least, either way. It depends on the assumption of what direction we point our shear force in. But at least magnitude-wise, we get the same answer. So for this one, the general rule of thumb I would say is take the side that has less going on, so there's less to draw, your equations have fewer things in them. So I would say take everything to the left of C to make this second, now internal free body diagram. So we copy exactly everything that's happening to the left of our cut. So we have to copy what is happening to the shaft at A. Well, we already determined that from the external picture. The bearing is exerting a force up of 367 newtons. AX we found was 0. I'm not going to draw it in this free body diagram since it doesn't impact it. And where we cut at C, we're copying everything to the left of it. We have some, but not all, of that distributed load acting. So if we go 1 meter in, and then we're cutting it at 1 meter, we can see half of that distributed load will be included in the picture, but the other half to the right of C, we don't see in our picture. And now where we cut through C, we couldn't see it in the external picture because our object was still intact and connected. But once we cut it, we can now expose what are the forces, what are the loads that are keeping that material together. So we cut through here, we can now see there's an internal normal force, I'll call P sub C. Our rule of convention is we always are going to have our internal normal force pointing out from the surface of our cut. So it's pointing to the right. We expose, and it's normal to the surface of the cut. We've exposed an internal shear force, I'll call V sub C, that's parallel to the cut. I'm going to assume it's up in this picture. Once we get further into the course and look at beam bending and combined loading, our assumption of direction will become more important. Here, if you say it's up or down, for the time being, it doesn't really matter, as long as you're consistent with your picture. Same thing with the internal moment. I'm going to assume it's a positive internal moment. But once we get to beam bending and combined loading, it becomes crucial to make the correct assumption of direction. Three new unknowns are introduced now, since we're in 2 dimensions and may cut through C. Questions on the free body diagram at C. 3 unknowns, 3 new equations we can get since we have another rigid body free body diagram. These equations will be simpler because one is only in the x, one is only in the y, and there's a moment. So in picture C, if we sum forces in the x direction, we have P sub C as the only force in the x direction. So there is no, the internal normal force is 0. That's not in tension or compression at C. In the y direction, we have the internal shear force, Vc. We have the force from the bearing on point A of 367 pointing up. And here from the picture, we have some of that distributed load. We have 600 newtons per meter, but in this picture, it's only 1 meter long down. So minus 600 times 1 meter. That's everything in the y direction. The only unknown is Vc. So the internal shear force, according to my assumption of it pointing up in this picture, is that Vc is 233 newtons. Finally, we can take the sum of moments. Usually it's going to be easiest to take it at the point that we cut, because that way the internal loads do not affect it. We'll have that equal to 0. So we have that internal bending moment m sub c. I assumed was positive. Plus 600 times 1 times 0.5. Since now the center of this piece is only 0.5 away from C. Minus 2 times 367. Solving equation 6, we get an internal bending moment of about 434 Newton meters.